Pluto is a far-off and confounding minor planet, once an individual from our planetary family. Anyway, continuous disturbing articulations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning revelation. They suggested that this chill world is on an intensive lesson with Neptune. Yet, how should this occur, and what may be the consequences of such a fundamental event? Are we seeing a flabbergasting impacted erraticism? Then again, is there something else to this oncoming, unending impact? Join us as we research the potential outcomes of a Pluto-Neptune impact. Pluto, a previous planet that was scaled down to a dwarf planet, is fundamental because of its odd circle, and it remains a subject of interest and study in the huge local area. As shown by later suppositions by leading specialists, Pluto's circle is perilously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential perilous accident between these two planets, which would represent a gigantic risk to Earth. How is such an event even conceivable? Pluto's trip around the Sun is not at all like that of some other planet in our close-by planetary framework. It requires a complex 248 years to finish a single circle, which truly means that since its discovery in 1930, it hasn't even finished one full revolution. Yet, the interest doesn't stop there. Pluto's circle is marked by its uncommon wound shape, wandering totally from the practically round circles of the major planets. What makes Pluto's circle significantly more momentous is its tendency of 17 degrees to the ecliptic plane. The course Pluto follows is fundamentally more extreme compared to other planets. One of the most fascinating pieces of Pluto's circle is its crossing point with Neptune's. For something like 20 years in each circle, Pluto, in reality, draws nearer to the Sun than Neptune, opposing what we'd anticipate from their positions in the planetary framework. This prompts the normal inquiry: why hasn't Pluto slammed into Neptune? The response lies in the gravitational impacts of different planets. The investigation of Pluto's circle began in no time after its discovery. Initially, stargazers endeavored to determine its unique circle. Not at all like different planets, whose circles lie close to the ecliptic plane, Pluto's circle stood apart with its lofty tendency and bended shape. The secret extended with the acknowledgement that Pluto's circle really does, to be sure, cross Neptune's. The study of Pluto's circle, in spite of these intricacies, is proof of the complexities of heavenly mechanics. The three-body issue in space is about sorting out how three bodies, like Pluto, Neptune, and the Sun, move and impact each other through their gravity. Pluto's circle is, as a matter of fact, fierce. Minor deviations in starting circumstances can lead to gigantic contrasts over lengthy periods. Anyway, these exceptional properties of Pluto's circle have been found to maintain stability over very lengthy timescales, keeping confusion under control. Ongoing reproductions have helped us comprehend how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's circle around the Sun. Jupiter's huge gravity is sufficiently able to keep Pluto on a consistent path for potentially billions of years. These factors are critical in keeping everything under control and maintaining consistency in heavenly mechanics. Without these components, our planetary system would be a place of far more significant turmoil and instability. Pluto's circle is a striking illustration of heavenly mechanics at play, showing both stability and confusion within our nearby planet group. The exceptional characteristics of its circle, affected by the gravitational forces of adjoining planets, particularly Neptune, highlight the complicated and dynamic nature of space. Predicting significant events, especially when it involves erratic orbits like Pluto's, presents huge challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainty. While mathematical simulations provide a robust means for understanding and predicting the future behavior of divine bodies, they also highlight the limitations of our predictive capacities. So, why are notable astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune, regardless of the different complex forces attempting to prevent such an event? Neil deGrasse Tyson and Michio Kaku, both famous figures in cosmology, have expressed worry about a possible crash between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a dazzling and crushing event in our planetary group. The impact would release a monstrous amount of energy, probably obliterating Pluto due to its smaller size and cold structure. Debris from the impact could scatter across the nearby planet group, potentially introducing a risk to other planets and their moons. For Neptune, such an impact could modify its ongoing environment and possibly its orbit, contingent upon the details of the accident. Michio Kaku, a notable theoretical physicist known for his work in string theory, brings an intriguing perspective to the conversation. His views on the future of space exploration and the association between divine mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational associations and orbital mechanics of divine bodies like Pluto can yield significant information for future space missions. This knowledge can help in exploring the planetary system more effectively, anticipating potential risks, and even planning missions to the outer reaches of our planetary system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other divine bodies, providing a guide to how we may approach and understand distant worlds. Concerning planetary science, heavenly mechanics, and theoretical physics, these fields are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the key principles of physics. If Pluto and Neptune were to collide, it would be a fantastic event in cosmology, offering an entrancing observational opportunity that might actually connect with string theory. String theory, a hypothetical framework where point-like particles in particle physics are replaced by one-dimensional strings, attempts to explain the major forces in matter. In the universe, the impact could create extreme conditions of energy and gravity, potentially leading to conditions where predictions made by string theory could become detectable. For example, the high-energy impact could provide insights into the behavior of key particles and forces under extreme conditions, a crucial area of interest in string theory. While the direct impact on Earth would be negligible due to our distance from the outer solar system, the scientific implications of such an event could be immense, possibly adding to our understanding of the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's peculiar dance around the Sun continues to enthrall scientists and enthusiasts alike, offering a window into the intricacies of heavenly mechanics. While its renaming as a dwarf planet sparked discussion and reshaped our understanding of planetary bodies, later revelations about its orbit have reignited interest in its role within the nearby planetary group. Neil deGrasse Tyson and Michio Kaku, two prominent voices in space science, have raised concerns about a possible impact between Pluto and Neptune, shedding light on the complex forces at play in our cosmic neighborhood. Their warnings underscore the importance of understanding the gravitational interactions and orbital mechanics that govern the movements of divine bodies. Pluto's orbit, marked by its unpredictability and steep inclination, defies traditional assumptions and challenges our perspective on planetary motion. Unlike the nearly circular orbits of its neighboring planets, Pluto's path follows a unique course, crossing Neptune's orbit at points during its long journey around the Sun. The gravitational influence of other planets, especially Neptune, plays a significant role in shaping Pluto's orbit and maintaining its stability over many years. Despite the tumultuous nature of its path, Pluto's orbit remains relatively stable within the broader context of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as suggested by astrophysicists Neil deGrasse Tyson and Michio Kaku, highlights the ongoing uncertainties and unpredictability in planetary dynamics. While such an event remains speculative and highly unlikely in the near term, the gravitational dance between Pluto and Neptune emphasizes the delicate balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, the study of Pluto offers practical insights for future space exploration missions. NASA's New Horizons spacecraft, launched in 2006, provided astounding pictures and data of Pluto and its moons during its historic flyby in 2015. The mission uncovered amazing details of Pluto's surface features, including vast fields of water ice and broad plains of frozen nitrogen, enhancing our understanding of the geological processes shaping the distant dwarf planet. The success of the New Horizons mission highlighted the technological advances and collaborative efforts necessary for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outer reaches of the solar system. These revelations have implications for future missions to explore other dwarf planets and trans-Neptunian objects, helping us understand planetary formation and evolution. Pluto's status as a dwarf planet has also sparked discussions about the criteria used to define celestial bodies within the solar system. The debate over planetary classification reflects broader questions about scientific taxonomy and the evolving nature of astronomical knowledge. While Pluto meets several criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Embracing Pluto's orbit expands our understanding of heavenly mechanics and planetary dynamics to the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are essential for developing theories about the origins of our solar system and understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary motion and the development of the Kuiper belt, a region beyond Neptune populated by small, icy bodies. Examining Pluto's orbit offers clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system's development. Understanding the complexities of heavenly mechanics can also inform future space exploration missions, including the search for habitable worlds beyond our solar system. By studying the movements of distant celestial bodies, space scientists can identify potential targets for future exploration and assess the feasibility of traveling to other star systems. The potential impact of a Pluto-Neptune crash, while highly unlikely, serves as a reminder of the dynamic nature of the universe and the unpredictability of large-scale events. As we continue to explore the outer reaches of the solar system and beyond, the study of planetary orbits and heavenly mechanics will remain a central focus for astronomers and space agencies alike. Pluto's orbit, which deviates significantly from the paths of other planets, offers valuable lessons about the complexities of planetary motion. The stability of its orbit over long timescales, despite its unpredictability, provides important insights into the balance of forces that govern the movements of celestial bodies. In a sense, the ongoing study of Pluto's orbit and its potential interactions with Neptune reflects the broader challenges of understanding the universe at large. With each new discovery and each theoretical model, we continue to refine our knowledge of the universe, uncovering the mysteries of distant worlds.